Alright everyone, let's get started. Today we are going to discuss two very important topics in projectile motion, the equation of trajectory and the equation of envelope. Now, I have already written a complete derivation on the board, so what we will do is, we will go through it step by step, and I will explain to you the logic behind each and every step. Please pay attention, because the way we think about this problem is actually more important than the final formulas themselves. So let us begin from the very top of the board. Here you can see I have written the basic setup for projectile motion. A projectile is launched from the origin point O with initial speed u at an angle theta with the horizontal. The horizontal component of velocity is u cosine theta, and the vertical component is u sine theta. This is standard, you have already done this in previous classes. The only acceleration acting on the projectile is g, downward, in the negative y direction. No acceleration along x-axis. This is our starting point. Now coming to the next part on the board. You can see two equations written here, one for x and one for y. Along the x-axis, since there is no acceleration, x equals u cos theta into t. Simple uniform motion formula, distance equals velocity multiplied by time. Along the y-axis, since g is acting downward, y equals u sin theta into t minus half g t square. This is the standard second equation of motion, s equals ut minus half at square. Now, these two equations are called parametric equations. Why? Because both x and y are expressed in terms of a third variable, the parameter t, which is time. If I give you a value of t, you can find both x and y. But what if I want a direct relationship between x and y? I don't want t in the picture. I want to know, for a given x, what is y? For that, I need to eliminate t. And that brings us to the equation of trajectory. And now look at the next section on the board. Step 1. From the x equation, I solve for t. T equals x upon u cos theta. Very straightforward. Step 2. I substitute this t into the y equation. So wherever I see t in the y equation, I replace it with x upon u cos theta. Now look at the simplification carefully. The first term becomes u sine theta into x upon u cosine theta. The u cancels out. Sin theta upon cosine theta is tan theta. So the first term simplifies to x tan theta. The second term, half g into t square, becomes half g into x square upon u square cos square theta. So the equation becomes y equals x tan theta minus gx square upon 2u square cos square theta. This is the equation of trajectory in one form. It gives you a direct relationship between x and y without any t. But we can write this in a better way. Look at the next part of the board. I have used the identity 1 upon cos square theta equals 1 plus tan square theta. This is a standard trigonometric identity. You should know this. Substituting this into our equation, y equals x tan theta minus gx square upon 2u square into bracket 1 plus tan square theta. Now, this form is written on the board. And this is a very important form. Can you see why? Look at this equation carefully. The variable that is changing from one trajectory to another is the angle theta. And in this equation, theta appears only in the form of tan theta. So if I write t equals tan theta, then this equation becomes quadratic in t. And that is exactly what I have done in the next section. To look at the board now. I have rearranged the equation to write it in standard quadratic form. Let me read it out. Gx square upon 2u square into t square minus x into t plus y plus gx square upon 2u square equals 0. Where t equals tan theta. This is of the form a t square plus bt plus c equals 0. And I have identified a, b, and c for you. A equals gx square upon 2u square. B equals minus x. C equals y plus gx square upon 2u square. Now, pause here for a moment and think. What does this quadratic represent? For a given point, x, y, in the plane, if I want to find whether a trajectory can pass through that point, I need to find a real angle theta. For a real theta to exist, t equals tan theta must be real. For t to be real, this quadratic must have real roots. And for a quadratic to have real roots, we need the discriminant to be greater than or equal to 0. B square minus 4ac greater than or equal to 0. This is the key idea. This condition will give us the envelope. Now look at the next section on the board. I have applied the discriminant condition. B square minus 4ac greater than or equal to 0. Substituting the values of a, b, and c. Minus x whole square minus 4 into gx square upon 2u square into y plus gx square upon 2u square greater than or equal to 0. Simplifying. X square minus 2gx square upon u square into y plus gx square upon 2u square greater than or equal to 0. Now I am dividing throughout by x square, assuming x is not equal to 0. We get 1 minus 2g y upon u square minus g square x square upon u to the power 4 greater than or equal to 0. This is the condition written on the board. Now from this condition, we will derive the equation of the envelope. Look at the next section. From the inequality. 1 minus 2g y upon u square minus g square x square upon u to the power 4 greater than or equal to 0. I rearrange to isolate y. 2g y upon u square less than or equal to 1 minus g square x square upon u to the power 4. Taking u square to the other side and simplifying. Y less than or equal to u square upon 2g minus gx square upon 2u square. This is the inequality. It tells us that y must be less than or equal to this expression. Now, the envelope is the boundary of this region. So the equation of the envelope is obtained by replacing the inequality with equality. And that is what you see written in the box on the board. Y equals u square upon 2g minus gx square upon 2u square. This is the 2D equation of envelope. Now, let me explain what this actually means. This equation represents a parabola. It opens downward. And it tells us that no projectile launched with speed u from the origin can go above this parabola. Every single trajectory, no matter what angle you launch at, will always stay below or on this curve. In fact, each trajectory touches this envelope at exactly one point. The trajectory is tangent to the envelope. Let me point out two important features from the board. First, the maximum height of the envelope. If I put x equals 0 in the envelope equation, I get y equals u square upon 2g. This is the highest point on the envelope. Interestingly, this equals the maximum height when you throw a projectile straight upward, that is, when theta equals 90 degrees. Second, the horizontal extent. If I put y equals 0 in the envelope equation and solve for x, 0 equals u square upon 2g minus gx square upon 2u square. Solving this x equals plus minus u square upon g. So the total horizontal width of the envelope is 2u square upon g, which is the maximum range. Now, look at the last section on the board. What if we are not restricted to a 2D plane? What if the projectile can be launched in any direction in 3D space? In 3D, we have the x-axis, the z-axis, both horizontal and perpendicular to each other, and the y-axis, which is vertical. By symmetry, the envelope should depend on the total horizontal distance from the y-axis, which is root of x squared plus c squared. So, in the 2D envelope equation, I simply replace x squared with x squared plus c squared. And I get y equals u squared upon 2g minus g times x squared plus c squared upon 2u squared. This is the 3D equation of envelope, and it is written in the box on the board. This surface is called a paraboloid. It is a 3D surface that looks like an inverted bowl. Every possible trajectory in 3D space, in any direction, any plane, stays inside this paraboloid. No point outside this surface is reachable. If you take any vertical plane passing through the y-axis and cut this paraboloid, you will get the same 2D parabola that we derived earlier. That is the beauty of this result. Alright, let us now summarize everything on the board. Starting from the top, we began with the parametric equations of motion. Then we eliminated t to get the equation of trajectory. We rewrote it as a quadratic in tan theta. We applied the discriminant condition b squared minus 4ac greater than or equal to 0. And from that condition, we derived the equation of envelope, first in 2D, then in 3D. The key takeaway is this: the trajectory equation tells you the path of one projectile for a fixed angle theta. The envelope equation tells you the boundary of all possible paths for all angles theta for a given speed u. The envelope is independent of theta. It only depends on u and g, and it represents the maximum possible height at any horizontal distance. I would strongly suggest that you go through the derivation on the board once more on your own. Try to reproduce each step without looking. Understand why we made the quadratic in tan theta. Understand why we applied the discriminant condition. If you understand the logic, you will never forget the derivation. If you just memorize the formulas, you will forget them in 2 days. Are there any questions? Yes, please go ahead. No questions? Alright then. Thank you for your attention. We will continue with applications of the envelope in the next class.